In section 6.3, we're going to look at the exponential functions. Again, coming from prerequisite courses here, you have some notion about the exponential function. You have seen this function before. We are interested again in the calculus of this function for us. That would be the derivative and the integral of the exponential function. So let's begin by defining the natural exponential function. The reason it's called natural because it's connected with the natural log. The connection it has with the natural log. So the natural exponential function, which initially is defined as exp for exponential, is a function so that the composition of the natural log of this function of x would give you x, and also it's a function so that when we change the composition to it and ln of x, we get x. So in other words, this is going to be the inverse of the natural log function. Okay, and of course you're given these respective domains in order to ensure that the composition will yield the result x we're looking for. It has to be within those domains. So this is the form that we're going to accept. Ln of y is equal to x. Also, this is another form that's permissible. Okay, so we're looking at the log form, the natural log form of that function. But this is a familiar form to you, exp of x. Even more familiar form to you is actually this form, next definition, which defines it to be in the form that we are familiar with. The natural exponential function is defined by the following rule, that e to the x is the function. Theorem 1 looks at a couple of properties of the natural log of e to the x. Ln of e to the x is x for all x real numbers, and e raised to the natural log of x is also x for x positive. Some of the properties of the natural exponential function, which by the way you can see on the graph, that's the graph of e to the x, and that is the graph of natural log of x. Notice how they are mirror images of each other with respect to the line of symmetry y equal x. Now these properties you can also observe them on the graph. So for example, property number 1 says or reads the domain is all real numbers. Well, this would be the domain of the exponential function. We're looking at the blue curve, by the way. Okay, so this is the domain, all real numbers, negative infinity to infinity. Remember, domain of a function means all possible x values, and range would be all possible y values. The function is continuous and increasing, means there are no breaks, holes, jumps, corners. Well, there may be a corner, but for function to be increasing. But anyway, not the exponential function doesn't have a corner. I was just saying the idea of continuity. That means there are no breaks, holes, or jumps in the graph of the function. And it is increasing, means it's always rising. In fact, it's monotone increasing over the entire domain. Item number 3 here, the graph is concave upward over the entire domain. And you can see that the concavity of the curve is in an upward manner. Okay, so those are some of the properties of this natural exponential function. And item 4, the limit as x goes to negative infinity means x gets very small, the function approaches 0. As x gets very large, approaches to infinity, the function shoots up, goes to infinity. That's what property number 4 indicates. Okay. Over here, the number e is defined such that if you take the natural log of that number, which by definition of, remember in section 6.1, the natural logarithmic function we defined to be the integral of from 1 to x of 1 over t dt. So if the argument of log is a number so that the integral from 1 to that number of 1 over t dt is 1, then that number has to be e. Okay, And that goes back to, again, when we talked about the very definition of the natural logarithm. In terms of the natural log function, again, ln of e here is a number such that the integral from 1 to e is 1. Okay, so this phenomena, that is the area under the curve becoming 1, occurs at this very special number e. That's when it happens precisely at e. Okay, so it just shows the role that e plays in that graph. Then we're going to look at the laws of exponents. They also hold for the exponential functions here. So e to the x times e to the y is e to the x plus y, and so on. Theorem 3 looks at the derivative, and Theorem 4 the antiderivative of the natural exponential function. Theorem 3 tells the derivative of the exponential function is itself. That's interesting. That means the rate of increase of the function is in exponential itself. Okay, very interesting phenomena. And the proof of that, actually very easy proof right here. So if I call y to be e to the x, then my definition of natural exponential function and its connection to the natural log, and that was right up here, right in here. And then we can write it as ln of y equal x. We are interested in taking the derivative. The derivative of ln of y from section 1 is 1 over y prime, because y is a function of x, as you can see, right? So we have to do implicit differentiation. The derivative of x is 1. Multiply both sides by y, and you can see here, of course, y isn't 0, cannot be 0, right? And it's not. And we know that because right up here, there you go. Hold on. It's just a moment. Let me clear this one up. Yeah, for e to the x, y isn't 0. Let's look at the graph. See, there's no x-intercept on the graph of this function. So, let's see. And then I cross multiply by y, and then, but y is e to the x, so I replace it, and I got this result. It's very easy to derive. Now, if u is a differentiable function of x, then the derivative of e to u is itself times chain rule. Theorem 4 is the last thing we cover in this, and then we look at the exercises. Theorem 4 tells us the antiderivative of e to u is itself. So the integral of e to u du is e to u plus c, and that again bears out from that relationship. If the derivative is itself, the antiderivative will give you the function. All right, and we are good. We are good to go, and we're going to take a look at these exercises now. Some of these I'm going to select. Okay, let's take a look at exercises number 2 and number 4. In both of these, we want to simply simplify the expression. Number 2, part A, is the natural log of the square root of e. So we can rewrite square root as e to 1/2, and then use the power rule of logarithm, natural log, to bring half in front. And this becomes 1/2 ln of e. And the natural log of e, of course, is 1. So this is going to be 1/2. Okay. In part B, ln of e to square root of e. ln of e to square root of e. This one. So for this one, we can actually bring square root of e to front of the logarithm and write it as natural log of e. Again, ln of e is 1. So the answer is the square root of e. That was number 2. Let's take a look at number 4, and in part A. natural log of e to x squared plus 1. Again, using the power rule of natural logs. Bring x squared plus 1 in front times natural log of e, and again ln of e is 1. So this simply becomes x squared plus 1. In part b of the same, we have e to the 2 ln of x plus cosine x. Now, 2 ln of x, remember, if we have something like ln of x squared, we can bring 2 in front, right? And that becomes 2 ln of x. Well, the reverse also works. A factor in front of a logarithm can appear as the exponent on the argument of the logarithm, so I can rewrite it as ln of x squared, putting the 2 back up as an exponent on the argument, which is x, plus cos x, right? That's what that becomes. Now, let's see, what are we going to do with this? Well, we can actually use the multiplication rule of exponents. We can split this into ln of e to the ln of x squared times e to cos x, right? Now, e to the ln of x squared, we know that e to ln of u is u, that property. So acting as a u is the x squared. And this I can write as x squared times e to cos x. And that's what that becomes. Okay, so we're done with number 4. Let's take a look at the next ones. Alright, so in exercise number 10, this segment we want to solve the equation. So I have written 10a, the equation is this. Now, next we're going to rewrite this using the definition of exponential function. Remember, if we have ln of y equal x, then e to the x equal y, right? Using definition of the natural exponential function. So I can rewrite this as x plus square root of x squared plus 1 is equal to e squared. Okay, and then I'm going to subtract x from both sides because I need to get rid of the radical. It's easier to isolate the radical because our next step is what? Squaring it, right? To get rid of the square root, you square it. So it's easier to square it now than previous step, because if you do previous step, you're squaring a binomial, and that's not going to get rid of the radical. Let's square both sides now. So I get x squared plus 1 is equal to, now I'm going to square the binomial, e squared minus x quantity squared, which becomes, once we square it, it becomes x squared, negative twice first by second is negative 2x, or let me put the constant first, 2e squared x plus e squared squared becomes e fourth. Okay, that's what that is. Now, subtract x squared from both sides, and you only have 1 on the left and the expression to the right. Now I can isolate. So 1 minus e to the 4th is equal to negative 2e squared x, right? Moving e to the 4th to the other side. So isolate x, I divide 1 minus e to the 4th divided by negative 2e squared. Okay, and then I can move the negative that is in the denominator in front of the binomial in the numerator, which causes it to look like this: e to the 4th minus 1, switch the signs by a positive 2. And there you go. That's how you solve for x. Okay, we haven't done any calculus yet. It's just working with exponential expressions. Let's do part B. In part B, the expression is x to 1 over ln of x negative x squared plus 1 equals 0. Now in here we just let's see, what are we gonna do? Probably the best way is to let's see, what are we gonna do here? Let's rewrite it like this. I'm gonna actually keep the term with x to 1 over ln of x and move the other two terms to the other side, okay, to the right side. Now at this point I'm just gonna take the natural log of both sides. Okay, this is what I mean. Take ln of x to the power of 1 over ln of x equals ln of x squared minus 1. That's what taking the natural log of both sides means. Now again, ln of x to a power, we can bring the power in front of the log, and that's just ln of x, and move the power, the exponent, in front of a log there. And equal on the right side is just ln of x squared minus 1. The ln of x on the left crosses out, and that would just make it ln of x squared minus 1 equals 1. And using, again, definition of natural exponential function, this becomes x squared minus 1 is equal to e to the first power. Okay, e to the first power, which is just e, right? So x squared is therefore x squared is equal to e plus 1, and we can take the square root. X would be square root of e plus 1. Okay, and the reason we have to use, I know we get plus or minus, right? But then let me just write that, since x is positive. Why is x positive? Because of the ln of x, right? Since x is positive, because ln of x, because of that. Remember, the domain of natural log has to be positive. And that is the answer to part B of this exercise. Let's take a look at some more. In exercise number 14, let's take a look at number 14. Show the functions are inverses of each other. Sketch the graphs of each pair of functions on the same set of axes. Okay, so first, to show that they're inverses of each other, remember, if they are, then we need to show, this is number 14, we need to show that the composition of f of g of x is x, and we need to show that g of f of x also, both of those must be x. So let's see if that holds. This is true for, in fact, all of these, not just number 14. That's what you need to show. So in number 14, then I'm doing the composition of f of, let me see, g of x is 1 plus ln of x. Okay, so let me use a different color for this. So f of that means, in the f function, I'm going to replace x. So it's going to be e to the 1 plus ln of x, and then of course there's a negative 1 next to that, which makes this just e to the ln of x, right? Because 1 and negative 1 add to 0. Those are opposites. And of course, e to the ln of x is just x because of the properties that we've cited. There. So that's the composition in one direction. The composition in the other direction, g of now f of x, that would be g of e to the x minus 1. And by that we mean, in the g function, we have 1 plus natural log of x, which is now e to the x minus 1, right? And this is 1 plus. Now, the ln of e to the x minus 1, we can actually bring x minus 1 in front of a log and just write that as the natural log of e. Okay, and of course the natural log of e is 1. So this is just 1 plus x minus 1, which makes x. So we showed in both cases that that property holds, right? It's not a property really, but that condition holds. Now, as far as the graph of these go, I'm gonna just do a rough sketch of the graph of these two. Let's see. The graph of e to the x is gonna look like this, right? That's e to the x. E to the x minus 1 actually will cause a horizontal shift of the graph to the right. So it's gonna look like this. Okay, this is a key point 0, 1, which moves now to 0 or negative 1 and 1 because there is a horizontal shift in the graph. So that's the graph of e to the x minus 1. Now, same token, the graph of g of x, which is 1 plus ln of x. Remember, the graph of ln of x it looks like so. This is ln of x. And the ln of x plus 1 will shift this up 1 unit, right? Now, let's see, right in here, the graph of ln of x goes through, because this point is 1, right? It goes through 1, 0. When you shift it up 1 unit, it actually coincides with this point on the exponential function. So it's going to look like so. That's what it's going to look like. That's the graph of ln of x plus 1. Or there you go, 1 plus ln of x. And you can see that they are indeed symmetrical. And if you graph it accurately, you can see that they will be symmetric with respect to this line. Okay. There is a number 14 for you. Now let's take a look at this next segment. In this next segment, we're going to take a look at the numbers 16, 18, 20. That is the limits. Okay, number 16. Let's begin with that one. In number 16, we want to find the limit as t approaches negative infinity of e to negative t minus 2e to the power of 2t divided by e to negative 2t plus 3e to 2t. So usually with limits involving negative exponents, what we do is we try to get rid of negative exponents. So in this case, I'm going to multiply top and the bottom by e to t. Okay, and doing so, and distribute. So this becomes the limit as t approaches negative infinity of. When you distribute e to t and e to negative t, those multiply to e to t minus t, which would be 0. Negative 2e to the power of 3t, and then in the denominator, actually, yeah, that's fine. I could have multiplied to e to 2t, but that's fine. So this is going to be e to negative t plus 3e to 2t. Okay, actually 3e to 2t and t makes 3t, right? When we distribute e to 2t, e to t makes e to 3t. Now, let's see, e to 0 is 1, true? So this limit is going to be, now let's take a look at this. In the numerator, as t approaches negative infinity, right, the numerator approaches 1 minus 0. Remember the graph, that was one of the 4 properties that we saw for exponential function. E to the x goes to negative infinity, approaches 0. So this part approaches 0. So does the part in the denominator approaches 0. And e to negative t, as t goes to negative t, gets very large, right? This is going to be kind of like infinity, right? It means very large. Again, it's e to negative t, but t is less than 0. So it's going to behave, it's going to get very large. And 1 over very large, which is infinity, is going to be 0. Okay. The key is e to negative t becomes very large as t approaches negative infinity. So there is a limit in number 16. Let's take a look at the limit in number 18. The limit as x approaches 0 from the right of 1 over 1 plus e to 1 over x. Now, e to 1 over x, okay, let's look at that one, the behavior of e to 1 over x. As x approaches 0, okay, as x approaches 0, well, that's like 1 over 0, so it's e to very large, right? So this approaches infinity. And the fraction is going to be 1 over infinity. The limit approaches 0 because the denominator gets very large. Notice 1 plus has no effect on the behavior of this function as because e to 1 over x approaches infinity, so plus 1 doesn't matter as x approaches 0 from the right in this case. The reason it's like, why does it x approach 0 from the right, is because when you look at the graph of 1 over x, here's x, this is 1 over x, here's 0. That's to make sure the exponent actually has a valid value. Because at 0, division by 0 is undefined. The function is undefined. That's why it's approaching 0 from the right. Okay, so that's number 18 for us. Let's take a look at the next one is number 20. In number 20, we want to find again the limit as x goes to 0 from the right, just like number 18, of e to 1 over ln of x. This time, because natural log of x at 0 is undefined, so we need to approach x from the right to be in the domain of the natural log. That's cosine of pi e to negative x. Alright, so for number 20, let's see. This is going to be, let's see. As x approaches 0, that's a constant, so we're just going to have 2. 1 over ln of x. As x approaches 0, remember the graph of natural log of x? As x approaches 0, the graph approaches negative infinity. So 1 over ln of x approaches 0, right? That's 1 over very small. So it's going to be 0, right? And the numerator is going to approach e to 0, which is 1, true? And the denominator is going to be 2 plus the numerator, e to 0 approaches 1. Okay. That's almost a 0. Remember, we approach 1, we're not quite 1, so it's kind of like that. e2 something that approaches 0 approaches 1. Now, with the cosine, let's take a look at the cosine. For e to negative x, as x goes to 0, e to 0 is 1. So pi e to negative x approaches pi, and cosine of pi is negative 1. So the cosine approaches negative 1. The whole thing approaches 1 in number 20. Good. And we have done those. Let's take a look at a few others. Alright, let's take a look at exercise number 24. In this segment, we just want to find the derivative of the function. So number 24, we have y is equal to x squared times e to negative 2x. So remember, all the previous rules of differentiation still in effect. we got a product, you're going to use the product rule here, so that's going to be 2x e to negative 2x plus x squared. The derivative of e to negative 2x, remember derivative of e to u is itself, times chain rule, the derivative of the function of x, which is negative 2x in this case, whose derivative becomes negative 2. And now I can actually factor 2x e to 2x times e to negative 2x, factor it. It's going to be 1 minus x. And there we have this one, right? Because there are common factors. I just factored the GCF. That's number 24. It wasn't bad at all. Let's try number 28. In number 28, we want to find the derivative of e to negative 2x times cosine 3x. Okay, times cosine of 3x, number 28. So again, we're going to use the product rule. Therefore, g prime is going to be the derivative of e to negative 2x is itself times negative 2 chain rule times cosine 3x plus first times derivative of cosine is negative sine 3x times 3, again its own chain rule, and that's what g prime x is. Now in here, to simplify, all I can factor is, looks like negative e to negative 2x. That will give me 2 cosine 3x plus 3 sine 3x. Okay, in this case we have combination in the form of a multiplication of 2 transcendental functions. That was number 28. Let's take a look at number 34. In number 34, we have ln of e to the x plus e to negative x. Okay, number 34, y is equal to the natural log of e to the x plus e to negative x. So y prime would be 1 over, so the entire parentheses, content of the parentheses acts as a u. So the natural log of u, its derivative is 1 over u. And then du is the derivative of the inside parentheses. The derivative of e to the x is itself. Derivative of e to negative x is itself, but then times negative 1 because of chain rule. The first one also has a chain rule, times 1, which I didn't write, is itself. So that's going to be e to the x minus e to negative x divided by e to the x plus e to negative x. And that's an interesting function, actually, the derivative here. What you call it? This turns out to be some kind of a hyperbolic function. Later on we talk about hyperbolic functions, but that's interesting, the way this function turned out. So that's all that is. That's the derivative in number 34. Okay. In number 40, we have e to cosine x squared, and then tangent, right, of e to 2x plus x. Okay, well, let's do number 40. In exercise number 40, y is equal to e cosine of x squared times tan of e to 2x plus x. So we're going to apply the product rule again, right? Therefore, y prime would be derivative of first. E to anything is itself, e to that thing, times, now derivative of cosine x squared. Now notice this cosine x squared, the way it's written, it's different. Cosine of x squared is not the same as cosine of x. squared. Okay, so it makes a difference how we take the derivative, right? Here the argument of cosine is x squared. So derivative of cosine is going to be negative sine of its own u times derivative of x squared, which is 2x. Okay, so that's just the derivative of e to cosine x squared. Don't forget that multiplies by tangent of e to 2x plus x. Okay, and then plus, this is going to be a long expression, plus e to cosine of x squared times, now we take the derivative of tangent. And if we recall, derivative of tangent is secant squared. So it's going to be secant squared of e to 2x plus x times chain rule. Notice how, by the way, my multiplication, I'm clearly using boldface multiplication sign. So like in this case, like that. The reason is because we cannot multiply these arguments by these coefficients. Okay, so derivative of e to dx is going to be 2e to 2x, right? Itself times chain rule, derivative of 2x plus 1. And there you have it. Now, in the way of simplification, in number 40, I can factor e to cosine, right? E to cosine of x squared factored out. Let's see what happens. So I got all of this now, and then we got all of that. Because the first expression is negative, I'm going to write that second, write this one first. So that's going to be, and when I write it also, I'm going to put the non-trig function in front. Just so again, there's no misunderstanding. Do not FOIL the binomial here. Okay? These two, do not FOIL them. Alright, so moving the binomial in front of secant squared, so I'm going to have 2e to 2x plus 1 times secant squared of e to 2x plus x. Done with this one. Minus, right? Minus. Now here I have 2x. Let me write that first. 2x comes to front. And you have tangent and sine. It doesn't matter how you write it. Let me write the sine, the less complicated one first. Sine of x squared. And then times tangent of e to 2x plus x. Close bracket. And there you have it. Okay. And that is the answer to exercise number 40. Let me grab a few more and we'll do more. Alright, let's take a look at exercise number 44. In exercise 44, we want to use implicit differentiation to find dy dx. Notice, it is explicit if you have y as a function of x, which we don't have. Now the assumption when we do implicit is what I just wrote, that y is indeed a function of x. So any time with implicit differentiation, any time you take the derivative with respect to y, there has to be a dy dx y prime because of this assumption, because we don't know what y is itself. So in number 44, x times ln of y, we're going to use the product rule, derivative of first, that's derivative of x, which is 1, times ln of y plus x times the derivative of natural log of y is 1 over y, but then remember, y prime. Anytime you take the derivative of y, there has to be a y prime. Plus, derivative of e to negative x is itself, chain rule, times negative 1. That's the derivative of a function of x itself, which is negative x. Minus y e y. That's interesting. That's a product rule. So for y e y, the derivative of y is going to be 1 and then y prime times e to y plus y times derivative of e to y is itself times y prime because of chain rule. Okay, and there we have it. Now we need to isolate y prime in number 44. Okay, so let's do that. I'm gonna collect all the terms with y prime on the left side. Okay, so on the left side I'm gonna have y prime and I'm gonna factor. First I have x over y, that's this one. Okay, and then on the other side, sorry, 0, derivative of 0, 0. So they end up being all on the same side, don't they? That's fine. So I'm just going to factor y prime here. Y prime from these three. So it's going to be x over y minus e to the y minus y e to the y. Okay, and the non-y prime items, we're going to ship them to the other side. So on the other side, I'm going to get e to negative x. That's negative of e to the x to e to negative x, move to the other side. Minus x minus ln of y. Okay. Now, let's see, what else can I do here? I see, actually, hold on. It's right in here. My mistake was group those together. Okay, actually this is x over y, which was brought in front. Okay, so that means I don't have it on this side. So that's just negative natural log of y. That's what this turns out to be. Okay, that looks better now. Okay, and the last step, the final step, is to isolate y prime. Divided by, let me go here, is x over y minus e to y, negative y, ey. And on the other side, I just have e to negative x, negative ln of y, right? That's what we have. Now, we do have a complex fraction. That x over y creates a complex fraction. That means you have a fraction as portion of a larger fraction right here. So I need to multiply top bottom by y. That is to get rid of complex fractions. We're not allowed to have complex fractions in the solution. So truly the final answer is going to be y prime equal, what you're looking at is just y times e to negative x, negative ln of y. And in the denominator we just get x minus y e to the y negative y squared e to y. So we get this rather complicated expression for y prime. Okay, and that is number 44 for us. Let me get more exercises for us to work on. Alright, so we're going to take a look at exercise number 48. In exercise 48, the question reads, show that the function y equal f of x is a solution of the differential equation. So here's the solution, and that is the differential equation, which I have moved over to the right. Now, remember, when we say a solution to a differential equation, we're not looking at like solution to f of x equals 0, like the answer is x equal to whatever. That's not how differential equations solve. The solution to a differential equation means equation involving differentials, meaning derivatives, would be to find the original function. That's actually the solution is a function. Notice this is the solution. That's what we want to show. So just want to clarify, we're not going to solve for x here or anything to get a number for x. We want to actually find a function. Now, we don't know how they got this solution. That's why you'll take a course in differential equation and you will learn how to do this. So for us, we just want to verify that it is indeed a solution. So your differential equation here involves y prime and y double prime. So it's a second order ordinary differential equation. That's what that is. Second order meaning the highest order in the equation, differential equation, has the highest order derivative is second order derivative. Okay, so I went ahead and actually did y prime and y double prime earlier. Okay, just in the interest of time, you can verify this. You can verify that this is indeed the correct y prime, y double prime. You need to start by the multiplication rule, take the derivative and simplify 2-3 steps for each of these, and 2-3 steps later you get the answers I have. So now I'm going to actually plug them in. So let me move down here where I have more room. So first I have y double prime, negative 4y prime plus 13y. Alright, so this is going to become, this is going to be a long line, isn't it? So that's e to 2x. That's the y double prime, cosine 3x, negative 19 sine 3x. That's just the first part. That's the y double prime. And then negative 4 times y prime. That's going to be negative 4 times e to 2x multiplied by cosine 3x, negative 8 sine 3x. Okay, and then it was plus 13y, plus 13. Y was the proposed solution, e to 2x times cosine 2 cosine 3x, negative sine of 3x. There you go, equals 0. We need to verify it, so I'm just going to put a question mark. Will all of that equal 0? Alright, the rest is some really simple extrapolation here. Just combine like terms and see what happens. First of all, everything has e to 2x in it, right? So we can divide both sides by e to 2x if you like. So e to 2x goes away. So I'm just going to combine a bunch of sine and cosines, right? Now, let's see. Negative 22 cosine 3x. I'm just going to look at cosines. 4 cosine 3x, 13 times 2. So that's going to be negative 22, negative 4, plus 26. All of that. Cosine 3x. Okay, and then let's take a look at sines. Same thing with the sines. We have 13 here, positive 32 here, negative 19 here. Plus, on the sine side of things, I have negative 19. Negative 19 plus 32, negative 13 of sine 3x. And let's see, what will that give me? That's going to make this, of course, that's 0. And this is 0. So we get 0 equals 0. That's how you verify it. Of course, the key is how do they find this solution? And that's what we learn in a differential equation class. The last two exercises. Exercise number 52. Find the absolute extrema of the function on the indicated interval. So we're going back to finding the extrema of functions, remember? And that was back in the beginning of this course. In exercise number 52, the equation is f of x is equal to e to 2x negative e to the x over the closed interval from negative 2 to 0. And because this is a closed interval, we have to also check for endpoint extrema, correct? If it was an open interval, we wouldn't have to do that, but it is a closed interval, so we will do that. And in order to find the absolute extrema, we need to do our first derivative test. So f prime of x is going to be 2e to 2x negative e to x, right? Derivative of first one is e to 2x times 2 chain rule minus the derivative of e to the x is e to the x. We're going to set this equal to 0, right? And when we do factor e to the x, that's going to make it 2e to x minus 1, true? And equal to 0, right? And here you can see, because e to 2x is e to the x times e to the x, so when you factor e to the x, you still have e to the x inside parentheses. All right. And so by 0 factor principle, e to the x is 0, or 2e to the x minus 1 is 0. Well, e to the x will never be 0. Remember, the exponential function does not cross the x-axis. So that can't be. No 0 comes out of that expression. Now, e to the x is equal to 1/2, right? Move 1 to the other side, divide by 2, so that gives you 1/2. And from this, using definition of natural exponential function, that means ln of 1/2, right, equal x. The natural log of 1/2, that's ln of 1 minus ln of 2 equal x. ln of 1 is 0, so x equals negative ln of 2. That's going to be the critical number. Okay, that's going to be the critical number of this expression. This is f prime. The only critical number in interval from -2, call that -2, and this is 0, close interval. Negative natural log of 2, let's see, negative ln of 2, I gotta use a calculator for this one. And that's going to be about -0.7. So right in here, that's what that is. That's negative ln of 2. It's about -0.7. Okay, so that's my critical number. Now I can pick a test point, right? I can pick a test point in this interval. So let's say I'm going to let x be -1. And then here you can let x be -0.5. Okay. Now f at -1 would be e to -2 minus e to -1. I'm going to, oh actually I'm sorry, I have to go to my derivative right here. So I'm going to go, sorry, take back. That's going to be 2e to e to the power of 2 times -1 minus e to -1. Now that's better. And I'll evaluate that on my calculator in a moment. And let me also do, before I go to calculator mode, put -0.5. That's 2e to 2 times -0.5 minus e to -0.5. Okay, so just to, before I go, let me prep this. Negative e to -1. This one becomes 2e to -1 minus e to -0.5. Now let me check. Okay, so here they are. I went in and evaluated those on my calculator, and I came up with the sign chart on my first derivative here. Okay, so my test point -1 yielded a negative number, so I have negative numbers in that segment of the number line. My test point -0.5 yielded a positive number, so I have positive signs from negative natural log of 2 to 0, which means the derivative is negative, means the function is decreasing, then increasing from negative ln of 2 at that point switches to increasing. Therefore, at negative ln of 2 there is a local min, okay, an L min. And I also have to test the verify for endpoint extrema. F at 0 is, and f at -2 is. Now notice these are the function values, and here I have f prime actually. Okay, sorry, because I'm trying to get the sign chart for the first derivative. So these, I plug them into my first derivative. I plug them into here, not the original function. But for these, I'm actually want to plug into the original function. I'm looking for endpoint extrema. That's why. Now f at 0 means e to 2 times 0 minus e to the x. That's e to 0. So that's e to 0 is 1 minus 1 or 0. F at negative 2, I'm plugging in negative 2 now. So it's e to 2 times negative 2 minus e to negative 2. And this one is going to be approximately negative 0.12. Okay, negative 0.12. And last, I'm going to do f at my critical point, which is negative ln of 2. Right, that's what I want to evaluate this. Now f at negative ln of 2, again I did that part also, and I got about negative 1/4. That's actually exact value, because for this one you do e to 2 times negative ln of 2 minus e to negative ln of 2. Okay, so that's going to be equal to e2. And negative 2 here, I'm going to write it as ln of 2 to negative 2. Okay, and move the negative here, minus e2 ln of 2 to negative 1. Now, e to the ln of 2 to negative 2, that's just going to be 2 to negative 2 minus e to ln of 2 to negative 1, that's just 2 to negative 1. 2 to negative 2, that's 1/4 minus 1/2, and that's negative 1/4. So that's how I got the exact value. Okay, so now if I look at these, then negative 1/4, that's negative 0.25. So comparing these three numbers now, negative 0.25 is indeed lower than all of these. Remember, on the number line here you have 0, negative 0.12, negative 0.25. So negative 0.25 is less than the other two numbers. And the question was asking for, let's see, find absolute extrema. That means absolute max and absolute minimum. So the minimum is going to be negative 1/4, and the max is going to be 0, and that's going to be the absolute max, and they are the extrema for this function over that closed interval. Okay, all right, so we are done with exercise 52. Let's look at one last exercise from this section and we'll be done. This last exercise, use curve sketching guidelines of section 3.6 to sketch the graph of a function e to the x minus x. Okay, so this is number 56 now. F of x, e to the x, and then minus x. Now, using curve sketching skills, remember the things we were interested in. Real quick, we were interested in x-intercept, y-intercept. We look for symmetry. We look for extrema. We look for peaks and valleys, first derivative test. We look for places where the concavity changes. That is the points of inflection. Then we look at the extreme behavior of the function, and if there are any asymptotes. So first of all, let's do the domain of this function, so I even know where I should graph this. Am I limited to a certain interval, or is the domain all real numbers? Well, the domain here, because e to the x, the domain of e to the x is negative infinity to infinity. Domain of x is negative infinity to infinity. And you have combination of two functions with same domain, So there you go. That's the domain. That's good. So there are like no vertical asymptotes because domain is all real numbers. It cannot have a vertical asymptote. Okay. Let's see. Let's find B intercepts. So the easier of those two intercepts is f at 0. That means when x is 0, so that would be the y-intercept. E to 0 minus 0, 1 minus 0 is 1. 0, 1. That would be the y-intercept. So the graph crosses a y-axis at 1. For the x-intercept, that's when we set the equation equal to 0, right? So we go e to the x minus x equals 0. Now, for this to happen, okay, let's see. This is the graph of e to the x at 1. And this is the graph of just x, right? Now, why am I doing this? Because this is the easiest way to tell you what I'm about to show. If I move x to the other side, see the dilemma is this. This is not an algebraic expression, so factoring isn't going to help me. You have a combination of a transcendental function and an algebraic function, so these never come out nice for the x, for the point of intersections, the x-intercepts, that is. So I need to look at places where these two functions cross. That would be the common point of intersection and hence the solution to the equation. Well, e to the x and x, as you can see, they never cross, so this can't ever happen. So that means there is no x-intercept. And that makes it really easy. Okay, so there's no x-intercept. So that means when there's no x-intercept, that means the graph is either above or below, right, entirely over the domain. So we'll keep that in mind. No x-intercept, but there is a y-intercept. Let's take a look at next extreme behavior. Let's take a look at the limit as x goes to infinity. How is this function going to behave? Well, e to the x, right? That's the limit of e to the x minus x as x goes to infinity. Now e to the x, and I know this is in indeterminate form, infinity minus infinity. Okay, because the exponential function supersedes the linear function, for this one we're going to say the limit is infinity. Okay, and I'm using the graph, so remember this is indeterminate form, and really to do this we need to talk about the Hopital's rule, but we haven't talked about Hopital's rule in this course, so I'm just going to do it the way I did, that the exponential function far exceeds the linear function. The end behavior is dominated by the exponential function, and for that reason it's infinity. What about the limit as x goes to negative infinity? So in other words, so far we know this. There you go. That's extreme behavior of this function. X approaches infinity. As x goes to negative infinity of e to the x minus x is. Now for the exponential function, as x goes to negative infinity, well, that approaches 0, right? That part of it approaches 0. And now this portion of the graph, the linear function, dominates, so that's going to be negative infinity. So the answer is going to be negative infinity. Okay, and let's see, as x goes to negative infinity, hold on, let me, negative infinity. Okay, so that part is right, and because we have a negative of negative infinity, so that would be infinity. Okay, so this is what we know. The function goes this way, the function goes that way. Remember, there is no x-intercept, so it has to sit above the x-axis. Crosses at 1. Pretty much you're looking at the graph of this function just by looking at the extreme values, the extreme behavior of the function, and the y-intercept. Okay, let me move this out of our way. Let's take a look at the other stuff now. The other things we look at is, again, asymptotes. There is no asymptotes in this one. If they were, they would show up right in here. Remember the way we determine the horizontal asymptote? We look at x approaching infinity, negative infinity. So we can say off of these two, there are no asymptotes, right? There are no asymptotes. What else? Let's take a look at now the extrema. For extrema, I need to take the derivative of the function. The derivative of e to the x is itself minus 1. Set it equal to 0 to get the critical numbers. So we get e to the x is equal to 1. And you can see by inspection here, or just rewrite it in log form. That means ln of 1 is equal to x. That's using definition of natural exponential function. By definition of exponential function, I can write it in natural log form. And ln of 1 is 0, of course, so that means x is 0. At x equals 0, that's the only critical number we have of the first derivative. So here's f prime. This is our critical number. Pick a test point like 1, pick a test point like negative 1. Okay. When x is 1 and we're checking the first derivative, so at 1, e to 1 minus 1. That's e minus 1, which is positive. Remember, e is approximately 2.718. 2.718 minus 1 is 1.718, which is positive. Negative 1, for negative 1, I get e to negative 1 minus 1. And that number is going to be less than 1 because e to negative 1 is 1 over e minus 1 less than 0. You can plug it in. I believe it's going to be 1 over e is like 0.27, something like that. Minus 1 is about 0.7. So it's going to be negative. So the function is decreasing and then switch to increasing. That means we have a local min at that point. So there's our extrema. Local min at that point. And let's next check out the concavity. Right, f double prime. I want to know whether the function is concave upward or downward. F double prime, that's the derivative of the first derivative, remember? That's the derivative of e to the x, which is itself minus 0. That's the derivative of 1. Wow, cool. The second derivative is just e to the x. Now, e to the x is always positive, right? It's always positive. So that means f double prime is positive from negative infinity to infinity. So this is always concave upward, right? And if you want to go through the routine, you say e to the x equals 0 to find critical numbers, but then e to the x is never 0, no critical numbers. And this is how you argue that it is always concave upward. All right, let's put all of these together now. So for this work, I'm going to, let me graph it. Hold on. Okay, so there you go. This is what I have, putting all that information, all that knowledge together. If you notice, here's the concavity of the curve. The low point is at this point is the lowest point. There is no x-intercept. The extreme behavior function approaches infinity. It's always concave upward, decreasing from negative infinity to 0, increasing from 0 to infinity. That's putting all of this information together for number 56. And with that, we are done with the graph of this function. Okay, next, let's take a look at some of these integration problems. Okay, so exercises 82 through 89. Let's begin with, I do even numbers just because you don't have the answers for them. So let's try number 88. In exercise number 88, we want to find the integral from indefinite integral of e to the x plus e to negative x quantity squared and dx. Okay, so what we could do is we can actually expand the binomial, and when we expand it becomes e to 2x. You square the first plus twice first by second plus you square the second one. Okay, now of course the middle term here is just 2, because e to the x times e to negative x, x minus x is 0, and e to 0 becomes 1. Now we can integrate individual pieces of the integrand. So the integral of e to 2x, just to show you that one, we can let u be e to 2x, so du is going to be derivative of e to 2x is itself times chain rule, derivative of 2x is 2, then dx. So we can actually write du divided by 2 is equal to e to 2x dx. Okay, and we can now rewrite e to 2x dx is just 1/2 du, right? That's what that is. And the integral of du is just u plus a constant, so it's going to be 1/2 times e to 2x plus a constant. That's just the integral of e to 2x. We'll do the same thing for e to negative 2x. Likewise, you're going to get a similar expression, except 1/2 that we have in front becomes negative 1/2. Okay, and here it goes. So the answer to the integral is going to be, as I just showed, 1/2 e to 2x. The integral of 2 becomes 2x, and the last one becomes negative 1/2 e to negative 2x plus a constant. And let's see, probably factor a 1/2 here. So we get e to 2x plus 4x minus e to negative 2x plus c. Okay, and there you go, number 88. Let's take a look at number 94. In number 94, let me write that integral. The problem reads, integrate, and the integral is that of negative 1 to 0 of 1 over 1 plus e to negative 2x dx. Now for this particular exercise, I just want to point something out here, because we're talking about making a u substitution. However, with this one, it's a little bit tricky in that, let me show you what I mean. If I let the obvious choice is let u be either e to negative 2x or 1 plus e to negative 2x, correct? So for example, if I let u be e to negative 2x, okay, then clearly du is going to be negative 2 e to negative 2x, right? Because the derivative of e to u is itself times chain rule, the derivative of u, and dx. Now here, if I because in the integrand I only have dx, right? I don't have this additional piece. So what I'm going to do is I'm going to divide by both sides. I'm going to divide it by negative 2e to negative 2x, and that's what dx is. And then if I replace in for e to negative 2x, the u substitution that we made, this becomes negative 1/2 du over u, and then that's what dx is. Please note, dx doesn't equal du, so it's not like you just always make dx equal du. Dx is whatever the other side turns out to be. So, but here's what I want to show you. I want to show you that this integral is now in the form of 1 over 1 plus u, right? That's our u substitution. And then instead of dx, I'm going to write negative 1/2 1 over u du. Okay, so if you look what happened here, I'm using it as indefinite integral. I know the limits of integration here are going to change, but because I'm not going to finish it this way, so I won't bother with that. Now at this point, the integrand is in the form 1 over u plus 1. Okay, this type of integrand, notice here, how am I going to integrate it? If I make another substitution, u substitution here, it's not going to work. So what we do at this point is we use the method of second semester calculus, which I'm not going to do because this is a first semester course. So at this point, let me just write down what you would have to do in order to complete this integral. You have to use what we call partial fraction decomposition. Okay, now you are familiar with partial fraction decomposition from pre-calculus course, so this name sounds familiar, but we're not going to finish it because that's something they do in the second semester calculus. They go through partial fraction decomposition. I'm not so we need a review of that, and that's why it's not in this course. And then you will continue working it this way. So for us, how are we going to do this? So what we're going to do is we're going to actually create something out of the integrand to get rid of the negative exponent, e to negative 2x, the negative exponent. Let's multiply both top and the bottom by e to 2x. Okay, so by doing that, I get e to 2x multiplied by 1 plus e to negative 2x, and then dx, right? So if I simplify this now, this becomes, the numerator, of course, is e to 2x dx, put x in front of 2 dx. The denominator, when you distribute, becomes e to 2x plus 1, because e to 2x times e to negative 2x becomes e to 0, and that is 1. That's the distribution. Okay, and then now, once we have it in this form, let's use our substitution. So if I let u now be 1 plus e to 2x, then du is going to be 2 times e to 2x dx. So 1/2 du is e to 2x dx, and that is exactly what's in the integrand. So we're good to make that substitution. As far as the limits of integration go now, let's see, when x is negative 1, when x is 0. We are plugging in negative 1 into our u substitution. So at that point, u is going to be 1 plus e to negative 2, and when x is 0, u is going to be 1 plus e to 0. And of course, e to 0 is 1, so that's just going to become 2. Okay, therefore the integral is going to be, the limits of integration run from 1 plus e to negative 2 to 2 of 1 over u du, and of course remember we have the 1/2 du, so I'm just going to put that half in there also. And the integral of 1 over u is natural log of u, right? Absolute value of u, but in this case I don't need absolute value because both the lower and the upper limit are positive. So then argument of the natural log will be naturally positive. So let's do the upper limit and then the lower limit. So the upper limit gives me ln of 2 minus the lower limit gives me ln of 1 plus e to negative 2. And there you have it. Oh, sorry, my ln of 2, I didn't write it well. There, ln of 2. And that's going to be the answer to this one. So it's much easier to use this clever insight. The catch is multiplying top and the bottom by e to 2x in order to create the appropriate u substitution for it to work. Otherwise, you have to use the method of partial fraction decomposition. Okay, so that's number 94. Next, let's take a look at exercise number 100. In exercise number 100, nice round number. Here we want to integrate. The question is integral from 0 to 1 of x e to x squared, and then e to the power of e to the x squared dx. Okay, now if you note, the exponent on e is exactly what this is, so it makes sense that we let the u substitution to be, I'm going to let u in this case be e to x squared. Du would be exactly the same thing, e to x squared, times the derivative of the exponent is going to be 2x and then dx. And of course we have x, we have dx, we have almost the whole part. So if I divide by 2, I get exactly what's in the radicand. That would be x e to the x squared dx. And that's what we want. So this is going to be the integral of the 1/2, the integral of, the reason for a half is here. It's going to be 1/2 the integral of e to u du, right? And the integral of e to u is itself. That's going to be 1/2 e to u. And the limits of integration, let's go here again. When x is 0, u is going to be e to 0 is 1. When x is 1, exponent is going to be e to the first power, which is e. So 0 to 1 goes from 1 to e in this case. And evaluation is from 1 to e. Those are our evaluation points. So this is going to be 1/2 e to e, right, minus e, and that's what you get. Okay, and we can of course factor e maybe from both terms, so this is going to be 1/2 e times e to e minus 1 negative 1, right? When we factor e from e to e, this is how we factor e from it. I'm going to multiply by e divided by e, so that way I can factor out the e on the outside. When we do factor e on the outside, then e to e over e becomes e to e minus 1, moving this e to the exponent. I'm sorry, to the numerator, not the exponent. So that's how I did that. And there you go. That's the answer to exercise number 100. And let's see, maybe do just one more here. Let's do exercise number 102. In exercise 102, we want to find the area of a region under the graph of y equal e to negative x squared from negative 1 to 2. Okay, so in exercise number 102. Okay, so we want to find the area from negative 1 to 2 under e to negative x squared dx. Okay, now the integral of that is going to be, again, if you let u be, for example, negative x over 2, then du is going to be negative 1/2 dx, right? So this is going to be the integral, negative 1/2. Well, actually, from this, we get dx is negative 2 du, right? So this is going to be negative 2 times e to u and then du. The limits of integration when x is -1 makes this 1/2. When x is 2, when x is 2, it becomes -1. All right, and because the limits of integration usually go from low to high, I'm going to make that a +2, right, and change the limits of integration from from -1 to 1/2 of e to u du. And this is going to be 2 times e to u from -1 to 1/2. And this would be 2 times e to 1/2 minus e to -1. And that would be the area. Now e to 1/2 is the square root of e, if you want to write it like that. So that's going to be root e, and e to -1, you can write it as 1 over e. So that's going to be the area in square units. We don't need to write, or we don't need to graph this, but if you did graph it, you get a function that sits above the x-axis, because e to -x squared is positive, always positive. Okay, now with that, we are done with this lecture.